Thank you for coming and bearing with any technology issues that might arise here. We are very happy to have our computer science seminar series for the fall starting today with Smaranda Muresan, who is joining us not from very far away across the street at Columbia. She is a research scientist at the Data Science Institute, as well as an Amazon scholar. And before she joined Columbia, she was, as I was, a faculty member at Rutgers. So we were colleagues twice now. She was in the School of Communication and Information there, where she co-founded the Laboratory for the Study of Applied Language Technologies and Society, and was also a recipient of the Distinguished Achievements in Research Award. So her research interests, as we'll hear today, are in the area of natural language processing around computational semantics and discourse, figurative language understanding and generation, argument mining and generation, and fact checking. She also looks at applications to things like education and public health, as well as building NLP technologies that can work for low resource languages that are often overlooked. She has several Best Paper Awards and is serving as a board member of the North American chapter of the Association for Computational Linguistics, and also will be upcoming program chair for their primary conference, ACL, in 2022. Or at least, sorry, I'm not sure if it's their conference, for the ACL conference.
Yes,
Okay, it is. I thought so, but then I
It
wasn't sure.
is.
So she'll be talking to us today about her work on knowledge-aware text generation, the curious case of figurative language and argumentation. Smaranda, thank you for joining us.
Thank you so much for having me here. It's very special to be here, and also particularly my first time to give an in-person talk after so long. So I'm happy to talk to you about our recent work, but I want to kind of give a research map and kind of teaching about the lab. My lab it's around computational pragmatics, right? So we are looking at understanding language in different type of contexts: social context, visual context, multilingual context. And some examples of the work on social context is looking at argument mining, understanding argumentative text, and also generation. For example, understanding how people are attempt to persuade other people, what constitutes a persuasive message, fact checking as well, argument reframing, where we looked at there is a lot of problems in discourse where people try to have rhetorical fallacy, for example, appeal to fear, and we want to make the arguments more trustworthy. We're also looking at figurative language, understanding and generation, looking at metaphors, irony, sarcasm, and impact on semantic analysis and emotion detection as well. We are also looking to get these foundational methods applied to NLP for education. And for example, we are looking at how can we help teacher understand whether students know argumentative writing, how to write a clear argument. We're also looking at NLP for public health. And here we're looking at NLP to understand the opioid epidemic using the social media analytics. In the visual context, we have some work, not a lot. I mean, most of my work is around the understanding social context. For the visual context, we're looking, for example, if you take pairs of images and their caption, try to understand the semantics of words by grounding them in visual context. And recently, we're looking at how changes in color impact the intensity of emotion towards works of art and why, and looking basically at trying to do generation as well there. And then finally, looking at really understanding language in a multilingual context, we're looking particular at poetry translation and low resource languages. And I want to say that a lot of this research is actually applied also in the courses that I teach at Columbia. One is the computational models of social meaning, which looks mostly around trying to do applied NLP to different areas like sentiment analysis, emotion, argumentation, persuasion, and so on. And the course of multilingual language technologies and language diversity, this is actually a class that was part of the Collaboratory where we co-teach computer science with humanities. And I'm co-teaching this with Isabel Zauk, who is from the Institute for the Comparative Literature and Society. And actually one of the research that we are doing, poetry translation, was coming out actually of this class, and it's an undergraduate student with one of my PhD students. So I want to First, before I start, in this talk, I'm going to focus mostly on some work we're doing recently in generation area. And I want to acknowledge the collaborators. First, primarily, one of my PhD students, Tuhin Chakrabarti, as well as Arkady, who was an undergraduate student, and he's now looking to come in the PhD programs. Ardit, who was a high school student, and now he's an undergraduate student at Georgia Tech, and some of my collaborators from other universities, UCLA, Google, and Germany. So let me tell you a bit the goals we had when we started thinking about working in generation. So the first was we want to generate figurative language to promote more creative generation output. So for example, you want to make dialogue agents more engaging, right? So you want to create more creative text, like use of metaphor or irony. You might make it more humorous. You also want to use those to be able to have a human in the loop approach for creative writing or argumentation, persuasive writing for students. So just to give you an example, this is a tool, StoryUmed is not our work, but is in a context of helping students produce creative writing. So for example, if someone starts typing, the sky was beautiful, maybe you will have suggestion of using a metaphor or simile, like the sky was blue like a canvas. And I want to motivate the whole work with a quote from Kundera: metaphors are not to be trifled with. A single metaphor can give birth to love. So I can say that's powerful motivation for the work. And we also looked not only at figurative language, but also argument. And we want to improve the model in NLP that are trying to understand arguments. And we are doing this through a generation model where we try to recover implicit premises in an argument. And I'm giving here the example, and you're going to see it later in the talk. So this is an example of an argument, implicit argument, that is from Sherlock Holmes' Silver Blades case. So you have this piece of text. A dog was kept in the stable, and yet, though someone had been in and fetched out a horse, he had not barked enough to rouse the two lads in the loft. Obviously, the midnight visitor was someone who the dog knew well, right? But here, in order to be able to have this argument where you have the claim and the premise, there is a missing premise, which is the dogs generally bark when a person enters in an area unless the dog knows the person well. So you kind of an explanation, why would you think this is actually a good argument? So one of our goals is actually when you have these implicit arguments with a missing premises to generate this premise, maybe to provide a better explanation why this is a good argument. We also look at improving the quality of civil discourse by reframing arguments in hyperpartisan or propagandistic discourse that contain logical or rhetorical fallacy. So for example, I mentioned an appeal to fear argument. You want to make the same content, more or less, but removing and reframing this appeal to fear with a more trustworthy argument. And we can see this, all of this technology, particularly in generation, as human in the loop instructional assistance. So you do want a human in the loop. You want to see the technology as just assisting the humans in the process. So, so what is the technology behind? And I'm going to briefly mention as I go, kind of in more details, but I would just say that the NLP trend right now is language models, right? Deep learning language model transformer, which basically a language model is trying to build a representation. We're trying to, let's say, for example, predict the next word in a sentence, or having a sentence with a mask word, trying to predict the word that is missing, right? So we're kind of learning these language models. And you see here all the vibe that exists right now in all the media, in New York Times, finally a machine that can finish your sentence, how I'm using AI to write my next novel, Meet GPT-3, it has learned code and blog and argue, right? So you see this portrayed in the media, and this is one of the technologies that is coming up. And I'm putting on the right, this is the media portraying the field. And this is a paper that just appears, you see here in August, from Stanford, who is building a center on foundational models. And it's all faculty at Stanford. It's opportunity and risk of foundational models. And if you look here, it mentions that AI is undergoing a paradigm shift with the rise of models, and these are the language model BERT, GPT-3, that are trained and on broad data and scale and are adaptable to a variety of tasks. So you see that these transformer model, language model, are becoming to be considered by the field as a foundational model, which everything is built on top of it. And we're going to look at some, the way that we are looking at, and I will argue we need to do more to really consider them foundational models. So for the work that I'm going to present, which is the generation work, the figurative language, so for example, how to get a sentence and make it metaphoric, or how to take a sentence, a literal sense, and make it ironic, or argument reframing, taking the one argument with appeal to fear and transform it in a trustworthy argument. We need training data, right? So you need models to be able to have examples of this type of phenomena and this type of translation from one to the other, but we don't have it. So we need to address the lack of training data for that. I will argue strongly for everything that people are doing in NLP, that you need to ground all of these have foundation in linguistic theories. All of these have foundation in argumentation theories. Can we use insights from those to build in our models? Another thing we need, knowledge-aware models. So language model can have an understanding of the word, but not really. So we need to enhance this model with common sense knowledge and the other type of knowledge, situating context and so on. And the fourth part, which I think is again critical, it's evaluation methods. How do we evaluate whether what the output is, it's truthful? It's truthful, for example, to the input. Is it faithful? What metrics should we use to be able to see that it's a high quality generation method? So this is the recent work we are looking at. So in figurative generation, we have metaphor, simile, sarcasm. We have some work on poetic translation and argument generation, argument reframing, generating implicit premises, and so on. And I'm focusing, because I don't have a lot of time, I'm just going to focus on two areas so that you understand how, but it's basically the way that we are approaching the problem is similar across the entire spread. So I'm focusing on metaphor generation and the generating of implicit premises in argumentation. So this was one of the paper, and this is with my student, Tuhin at NACL on metaphor generation. So the task is you get a literal input sentence and you want to generate the corresponding sentence. And to just start the work, we made a simplifying assumption. We said, let's focus on verbs. And because they are always the key components of metaphoric expression. So you see here, let's say literal input 2, the window panes were rattling as the wind blew through them. And you want to generate a metaphor, the window panes were trembling as the wind blew through them. So that's the task. Take a literal input with a verb in a literal sense and generate the metaphoric sense of the verb. So again, addressing the key challenges is how, again, the lack of training data. And in our case here, it's literal and metaphoric, right? So this is the type of data we need to be able to train a model. But we also want to impose to make sure that what we generate as a metaphoric sentence has the same semantic as the literal. You don't want to generate a metaphoric sense that it doesn't actually have the same semantics. And then how to overcome the tendency of this language model to just produce literal text and not metaphoric, because a lot of the language model are trained on newspaper, web in general, much more rather than really literally text. So they tend to generate literal text, not metaphoric one. So here is the insight. So when we start thinking about, we said, well, there is a lot on metaphor, either in the philosophy of language or in linguistic. And the first things we looked at was the theoretical relation between metaphors and symbols. So a metaphor is not language. It is an idea expressed by language, an idea that in its turn function as a symbol to express something, right? So this, keep in mind this insight, and it will become clear where we use it. So our approach, so the first, we want to address the first issue, which is generated parallel data to train our models. So what we did, we said, well, let's identify metaphoric sentence first, and then generate the opposite problem, right? So you identify metaphoric sentences, and we generate the literal equivalents that are semantically consistent. And this way, we build this literal and metaphoric parallel data. Once you have that, you can train a model, and I'm going to go briefly about what the model is, but then you train a model, a sequence-to-sequence model, now starting from the literal sense to produce the metaphoric sense using your generated data. And then we're going to look at assessing the quality of the generated metaphor, both in intrinsic evaluation and in a task-based evaluation, when I'm going to present. And I also want to say that please interrupt anytime you have questions. If there is any question or I go too fast, please let me know. So the first task, right? So the first task to create the parallel data was to identify metaphoric verbs. So what we did, we look at the Gutenberg poetry corpus, which is a large data set. And for example, you can have sentences that have metaphors, the house where love had died. And we identify these metaphoric verbs. And again, you use here a language model to be able to do that. And we fine-tune this model. I'm going to talk a bit more about this a bit later when I'm going to explain a bit the language model and knowledge models. But we take this language model and then we fine-tune on a data set that was annotated with metaphoric verbs. So we take a model to automatically detect the metaphoric verbs in sentences. And we choose the sentences where the model predicts with a very high confidence score. And then we look at this manually to look at some of the sentences as well. So we do this and we automatically identify metaphoric verbs. And now the task is, if I have this set with metaphoric verbs, I want to do first the opposite in order to create the data. I take the metaphoric verb and I want to convert it to a literal meaning that is semantically consistent. So if you look at the sentence, the house where love had died, you want to generate the house where love had ended, right? So where in this case is the same meaning, but then the metaphoric verb died in that context is translated in the literal sense, ended. So how do we do that? So first here we do, as I said, the language model. You call it masked language model in filling, which basically means you take these large language models and you mask the metaphoric verb. So in the case where I had here, the metaphoric verb was died, what we do here in that models, you mask this word and you give it as input to the model. So the house where love had, and then you have this mask. So what the model does, try to predict, because it learned from a lot, a text, try to present what is the most probable word to come after this, right? So I can say the house where love had, and you have a lot of candidates. So here you can have where the love has started, originated, been, ended, and so on, and you get it with a probability score. So then what we did, we also we reversed the metaphoricity score for that. So basically we want words that are mostly used in a literal sense. But in this case, what you notice, right? So you have here, started, originated, been, ended, and so on. These are the candidates. But which one do I choose now to pair with my original metaphoric sense, right? So so this is where what we actually want. So in order to be choosing these verbs, started, originated, been, ended, we want to choose the verbs that when you put it in the context of the sentence has the same meaning with the metaphoric verb, right? So the house where love had died. So this is our second step, which is semantic consistency. We want to make sure that these literal sense are consistent with the metaphoric verb meaning. And for this, we use what it's recently called adaptive knowledge model, not language model, and I'm going to explain what it means. Which are basically these large language model fine-tuned on common sense knowledge like ConceptNet, and we use the symbol of relation. So here is where we use the insight, right? So we said, okay, I want to take this word, and you're going to see in a second how we use it. The house where love had died, you give it input to this Comet model. I'm going to explain in the next slides. It will generate that this is a symbol of loss, loneliness, despair, sadness, and sorrow, right? So this is what the model generates. So let me go just briefly in our parentheses to explain a bit what these knowledge models are. So basically, as I mentioned before, right? So a language model, you take this large text corpus that can be, you know, entire Wikipedia, news article, basically a lot of billions and billions of, you know, of a large corpus, and you build and you train these models, which basically a language model, what it does, it tries to take a sentence and predict the next word. That's kind of the, but in this very complex architecture, which is a deep learning architecture. But this is what it tries to do, to try to predict the next word. So this is an example of one of these models based on GPT-2. I wanted to learn to sail, so I bought and then it generates based on probability, what is the most likely words to come. So in this case, boat, sail, small, and so on. I wanted to learn to read, so I bought a book, and so on. So when you look at what it generates in this simple scenario, it seems like, well, maybe they have an understanding of some sort of knowledge in those language model, right? Because it say, well, if I need to sail, the most likely word it generates is boat. If I say read, the most likely the word is book. But is this enough? Can we actually enhance this language model, which seems to have some knowledge built inside it, but basically to augment them and build it more with common sense knowledge? And this is one of the research that is done at University of Washington on this comment model. That's exactly what they try to do. They try to take this language model and then a big, large common sense knowledge like ConceptNet, and try to, all this pre-trained language model, to train them again on these knowledge sources. And the way they do it, that almost translate this ConceptNet knowledge, like person sails across ocean, requires to buy a boat. It translates these triplets in a language, and then they continue training on this knowledge. So that's more or less the idea of incorporated of building this knowledge model. And this is the comment that was developed at University of Washington, right? So the idea is that language models contain some implicit level of knowledge, and you want to retrain them on some knowledge structures, ConceptNet, or any other type of knowledge that you have. And then you basically build a better model, which is called adaptive knowledge model, that contains some sort of information about common sense. So let's go back to our application. So we take this, as I mentioned, the metaphoric verb, the house where the love had died, and we pass it through this knowledge model Comet, and it generates is a symbol of loss, love, despair, and so on. So now what we do, we take these candidate literal sentences and pass them through Comet, right? So one, you saw at the top of the list, the word that was the candidate was started, right? So the house where love has started. Now, if you pass it through this Comet model, gives you is a symbol of love, life, marriage, romance, and passion. And if you look at the other one, the house where love have ended, it is symbol of loneliness, loss, despair. So now we compare this symbol of, right? So what is the meaning here and here versus the meaning that was before? So it's very clear that the house where love have died is much more closer semantically with the house where love have ended, because it's the same, basically they encode the same symbolic meaning. So that's what we did, and that's how we actually used to generate our training data, right? So again, as a recap here, we first identify metaphoric verbs, which we generate the literal sense using this mask language model and with a semantic meaning overlap from Comet. So this is the way we create large parallel data of 90K training example and 3K of validation. So again, as I mentioned, you take the metaphoric, you do mask language model to generate candidate. We use this Comet to choose the one that are semantically similar, and we generate the literal meaning. So once we have that, we then use an off-the-shelf, which is called a sequence-to-sequence model. So right now, what you take this literal sentence, and you want to obtain the metaphoric sentence. So there is this model that was built in 2019 called BERT, which is again a transformer model, but in this case, it does a sequence to sequence. So it takes an input sentence and it translates in an output sentence. So that's an decoder architecture, more complex, but that's the idea here. You have an encoder part where it takes your input, I wonder, hopelessly, and it generates, which is an autoregressive decoder that generates the output. So we fine-tune this model on our data. And then once we train this model, then we can just use it, giving a new sentence in the literal sense, the black desert covered in silences. It will generate, hopefully, a metaphorical sense, black desert gripped in iron silences. And we added in the end here another part, which we call it a discriminated, because as I mentioned before, language models tend to generate more literal sense. So what we did is that in this model, if it generates candidate verbs, we also score them again on metaphoricity, and we choose the one with the higher score. So this is the idea. This was the idea that, that we have. And we did a lot of, we did a test, and the first intrinsic evaluation we did it with both on, we focused particularly on human evaluation. So we take literal sentences from different data sets, and we asked two literally experts. So one was a poet and the other one was a novelty writer. So we asked them to take this 150 example and generate metaphors for them. And we compared them with some state-of-the-art model, metaphor masking, that was in 2020. We also compare with just we call it lexical replacement. So it's basically just our technology how we build the data set, right? So mass language model with Comet. And for evaluation, we use fluency, meaning preservation, creativity, and metaphoricity. So we had humans to evaluate the output generation on these 4 criteria, and we use Amacal Mechanical Turk to do that, and a scale of 1 to 5. So these are the results. So this, of course, the first 2 are the humans that we're doing. We look at we also evaluate through Mechanical Turk how the human generated output was. So the Turkers were actually, we're looking at the literal and the generation, and in the generation we had the human translation at the baseline and our model without telling them which is which, and we shuffled so they don't come in the same order. So people kind of try to figure out and try to. So of course the humans are much better, which is it's good. But then our model also does pretty decently on metaphoricity and creativity, and basically on all the fluency and meaning preservation, comparing with the baseline models. So this is some examples. My heart beats when he walks in the room, and one of the humans says my heart skips when he walks in the room, and our model generates my heart jumps when he walks in the room. So it's still it was ranked fairly high. And then another example, after a glass of wine, he relaxed up a bit. After a glass of wine, he loosened up a bit, which is actually the same as the human that was generated on that example. So this is one way to evaluate. We said, well, okay, that's fine. We take this. I mean, one of the main issue in generation is going to come up as a theme is that because we need human evaluation, the scale of the evaluation tests are very small. So we tried to do something else. We also want to do in a task-based evaluation. So we took poems and we keep them from the Reddit OC poetry, and we limited to 4-sentence stanza. And we replaced some literal verbs, 1 literal verbs in the poem with one that is generated by our method with the metaphoricity score. And then we asked Turkers where the original version or the rewritten version is better. And the rewritten version with the metaphoric verb was 68% considered better than the original one. So we tried to do that in a task-based evaluation. Try to see how much. So this was our first attempt to model metaphors. But then we said, well, what are we still missing, right? So we use some insights that metaphors and symbols, there is this relation, but there is a whole literature in computational, especially from the linguistic side and the philosophy of language, which is called conceptual metaphor theories, right? So in this case, they hold that we use conceptual mapping between domains, which are conceptual structures, to generate linguistic metaphor. So metaphoric mapping consists of a source and the target conceptual domain, where the source domain is the conceptual domain where we draw the metaphoric expression, and the target domain is the domain that we try to understand. So let me give you an example here. So this is one of the classical mappings. Argument is war, and you have the literal sense saying they argue against the contract, and the metaphoric is they fought against the contract, right? So you have the argument is your target domain, is the literal sense, war is your metaphoric sense, right? So they fought against the contract. They supported their new proposal, they defended their new proposal, right? So you use this notion, and you have, a lot of, metaphor, like, life as a journey, life as a struggle, and so on, right? So you want to kind of capture this and guide the metaphoric generation to take into account this target and source domain. So we continue our work on that, and we collaborated with some of our colleagues in Germany for that. And here is, the task is similar, but we made some constraints on the task. So given a literal input sentence that evokes a target domain, we want to generate a metaphoric sentence that evokes a particular source domain. And I'm going to give you an example. So this way we apply these conceptual metaphor theories. Again, we focus particularly on verbs as a simplifying assumption. So why this is interesting? So first, you can get a literal sentence, the party ended as soon as they left. And you can generate many metaphorical sentences depending on how the source domain you want to evoke. So the party ended as soon as she left. If you want to evoke something about death, the party died as soon as she left. An explosion, like the party exploded as soon as she left, changed position, the party dwindled as soon as she left, right? So you can actually generate different ways of generating metaphors depending on the time of the source. So in the previous work, we only had one literal to one metaphoric. Here, now you can actually control the generation to take into account what type of source domain you want to use. So basically, the approach, and I can go a bit more quicker here, but the approach is very similar with what we had before. So the automatic generating of the parallels data is very similar with what we have. Identify metaphoric sentence, generate the literal meaning. What we do add here, we label these metaphoric and literal verbs with source and target domains. And then we use those information into the sequence to sequence models. And so you can see that's not, it was just a small improvement here. So we take the way that we generated before, the house where love have died, and the house where love have ended here. And now how to build the source and target domains. What we do is we take a proxy for this conceptual mapping, which is it's a resource in and a conceptual approach to semantics in NLP called FrameNet. So what FrameNet tries to do is take verbalization and map to conceptual structures. So if I say, for example, Mary bought a book from John and John sold the book to Mary, it's actually the same meaning. And the frame is a contractual, buying and selling event, right? So they tried actually to capture this in the frame semantics. So you have this conceptual meaning where many verbalization will map there. So that's what we use for the source and target domain in this case. So in our case, we're going to have the house where love have died with the frame death, and the house where love have ended with the frame goes to end. And this is this getting from this resource. So as before, right? So what we do, again, we just add this component here. And now we use the same architecture, the sequence to sequence model that I mentioned before, but we add this information as a guiding control for the generation, where we mentioned this is the particular verb you want in this particular, having this particular semantic goes to end, and we want to generate something that will evoke the source domain death. And then we fine tune the model on that. So now, as once you train your model, now you give a new sentence that is unseen in your training data, and let's say, for example, I want now to get he resisted the panic of vertigo, where I know that resist is self-control, and I want now to generate a sentence that will be the same semantically as this one, and then evoke a source domain quarreling. So now you generate he fought the panic of vertigo, right? So you give as input now to the model, not only what sentence to replace, but also what will be the source domain that you want to your metaphor to evoke. And we compare our models with a simple lexical, unsupervised lexical baseline and with our previous model that I explained before. So we did many evaluations. I'm going to talk a bit one where we look at the gold data. So we have a test set that was developed again from Gutenberg Poetry Corpus. And we construct the literal meanings and label them with frame semantics. And then we test also on unknown metaphors. But then for the time being, I'm just going to focus on the results on the test set. So we look both at automatic metrics to evaluate, and there's also human evaluation. For the automatic metrics, we look at the distance from the gold. So we have a literal sense and the gold metaphor and our generated sentence. And we try to see how semantically similar they are to the gold matrix. We're using an automatic similarity matrix for that. And then we also have human evaluation, again, 3 experts, and we have 2 criteria, metaphoricity and relevance to the source domain. On a scale of 1 to 4, 4 being good and 0 unintelligible output. Right, so we see that our model, which we call it BERT here from Conceptual Metaphor, does good on both the automatic metrics. So here, distance from the gold means lower, it's higher. It's better, lower is better because the distance is smaller. And here we looked also at the percentage of time that the generated metaphor is actually the same, exact same as the gold metaphor. So we have that in almost 30% of the time, our was the same as the gold. And then we did the human evaluation based on metaphoricity and relevance to source. So what we see that on metaphoricity, our model now does a bit better than our previous model. So even the previous model, the highest number is 4, was doing okay. It's a slightly better, but where you see the big discrepancy here is the relevance to source, right? Because the first one was not taking into account source information and our new model does. So that's where we have better. So these are some example again, a dim aurora rises in my east. And the first is basically in this, you want to generate a metaphor that evokes the domain residence. So the gold is a dim aurora lives in my east. Our previous model generates a dim aurora hangs in my east. That's not really quite grammatical. And then the new model, it's basically generates the same as the gold. And here is the resisted the panic of vertigo. The gold is he fought the panic of vertigo. It has to evoke the quarreling domain. Our model generates he disputed the panic of vertigo, which it's more in line with quarreling than before. So yeah, so this was the work we've done on metaphors, and we have similar work on simile and sarcasm, very similar kind of approaches to look at that. But I want to go briefly on the work on generating implicit premises. And this is very recent. It's going to appear at EMNLP in November. And this was a work that was with the high school student we had last semester. And now he's an undergrad at Georgia Tech. So we had a very, our work, this actually comes from the work we have doing a lot in argument understanding. And the big problem that exists right now in all the models that are trying to understand arguments from text is this, what is notion, which is called an enthymeme, which is an incomplete argument found in discourse where some components are explicit, but other propositions are left implicit and need to be filled in to fully understand what the argument is, right? So this is the Sherlock Holmes Silver Blaze case that I mentioned before, right? So you have here the claim, the midnight visitor was someone who knew the dog well, and then you have the premise, but then in order to really understand why the premise supports the claim, there is this missing implicit knowledge that exists that you want to discover to be able to make sure that really the model understood the argument. So again, the task we had was a slightly simplified assumption. We consider an enthymeme, which is this implicit argument, where is given just a claim and a conclusion and a claim and the premise, right? So it's only 2 sentences, the claim and the premise, and we want to generate this missing implicit premise. So the key challenges you're going to recognize from everything we had before is the missing of the large scale data, right? So in here, what you need to be able to build this model, you're going to need example of these implicit arguments with the arguments where the implicit premise is filled in, right? So it has to be generated by human or, so you don't have that. So how are we going to go about building models for that? And then we also need, of course, common sense and word knowledge to be able to generate this. So again, coming to the second things that I mentioned we need when we're trying to solve problem is to look at insights that are coming from theoretical, either linguistic or argumentation. And in this case, one is the incomplete arguments in naturally occurring discourse more often than not require abductive reasoning, which are plausible explanation rather than the more strict form of reasoning based on deductive logic. So this is coming from argumentation theory. And then one of the examples is the Silverglass case that I mentioned. So what we did, we said, well, okay, so let's look at this problem as an abductive reasoning task, as an auxiliary task to help. And what happened was that in 2020, last year, again, the University of Washington group built a very large data set, and I'm going to explain a bit later, on abductive reasoning in narrative text, right? So we can use this data as an auxiliary task for our models. And then we also want to use knowledge, common sense knowledge, in order to be able to enhance our models. So let me explain a bit what this is. So first, the task is you have a claim, vaccination should be mandatory for all children, and the reason vaccination save lives. So you want to find this missing premise that links the reason to the claim. So the first one is when you apply this sequence to sequence model that I showed before, BERT, which is called BERT. This is what the line here, zero shot, means. You can see that this model will just say vaccines save lives, they save money, which is basically just repeats what the reason is. There is nothing, right? So your input is vaccination save lives, vaccination should be mandatory for all children, and these models are generating vaccines save lives, they save money, which is really not doing anything, right? It just repeats the reason and adds something that is not relevant to the task. The model then takes this abductive reasoning task and then kind of fine-tune the model on that. It gives vaccination are the best way to protect children. So again, here you'll see a bit more, something that is relevant on implicit premise. And our model that takes into account both fine-tuning on the abductive reasoning and using common sense knowledge. And I'm going to show in the next slides how we do that, generate vaccination are the best way to prevent childhood diseases, which are better explanations for the link between the reason and the claim. So just a bit of the description of how this large abductive reasoning in narrative text data set was built. So this was generated using crowdsourcing. So what they did is that they took short stories, which is basically they took the first sentence from the story and the last sentence from the story. And they asked workers to generate plausible and implausible hypotheses that explains the two observations, right? So I have a story at the beginning, then it's a narrative and the last sentence from the story, and they ask people to generate implausible and plausible hypotheses to explain this observation. And then they did some sort of adversarial filtering to pick up the more challenging examples for the models. So this way they generated these 50K training instances, which is not exactly what our task is, but is closely trying to explain how can we go from one observation to the other. So how do we use it in our model? It was very simple. We just take our case, which was the reason and the claim, the reason and the claim. And in the output, we used so this was the output one was one observation, and then we added and since hypotheses, and then the second observation. So this was actually building from their data set. We added this discourse marker to make the text more coherent. right? So I'm giving here the example that comes from their data set. Amy was looking through her mother's old scrapbooks. Amy realized her mother had dated her history professor. So this was the input in the data set they had. And then what people, the crowdsources come up with were saying Amy was looking through her mother's old scrapbooks. And since Amy found pictures of her history professor and mother together, Amy realized her mother dated her history professor, right? So this was generated automatically by people. So this was the hypothesis people had. So basically what we did, we tried this existing data set and we tune a model on that. But then we also said, well, common sense knowledge, particularly for argumentation, is really important. So what we did, we took this COMET knowledge model and we took a version of it that is actually taking into account the discourse. So let me give you an example here. And this is taken from the paper, from their paper. So let's assume we have this sentence. Ella walked around the property and we wanted to generate what was Ella's intention, right? So you say Ella walked around the property and her intention was Ella wanted to find Ella wanted to, for example, get exercise. So if we're only looking at this particular sentence, you might generate very likely that she wanted to exercise. However, if you're looking at the entire discourse, saying the water bill at Ella's house had been high, Ella walked around the property, now it's more likely to say that Ella wanted to fix a leak or fix the pipe rather than just saying that she wanted to get exercise, right? So you want to generate this contextual knowledge when you not only look at the sentence, you also look at the entire discourse. So for our purposes, we did that. And basically we take this data set that we have initially. So what we do is actually we add this common sense knowledge that is given by this discourse aware models. So we took what you saw before. Amy was looking through her mother's old scrapbook, and then here is the common sense to find something. Amy realized her mother had dated her history professor, and then we generate the same things, right? So we added this information because she wanted to look in the scrapbook with a particular intention, right? So you want to look for something, and that's kind of the information we added in the data. So now to evaluate our model, we use several data sets. And again, here, because it's very expensive to create, we use them just to test our models. So these were generated by humans. The first one was coming from a shared task done in our conferences on argument reasoning comprehension. And here you have these 1,600 enthymemes, which are these implicit arguments of a claim and a premise and the missing premise. We also took another one that comes from discussion forums, again, with human-generated implicit premises. And the third one was, again, a very small data set with human-generated implicit premises. And we evaluated the model. So this is the main model we had, where we use both the abductive reasoning task and the common sense knowledge. We remove the common sense knowledge, so we compare this bar sequence to sequence model with just fine-tuning on the abductive reasoning, and the other one is just this big pre-trained model, language model in what we call zero shots. So it's basically just model trained on completely different tasks. So for evaluation, we use blue metric and BERT scores, but so I don't want to enter detail, but these are basically the standard metrics that try to evaluate generation output and how good they are with the reference translation, right? So for example, they were used initially in machine translation, where you have the translated text in English, and then you have a reference translation done by a human annotator, and they were trying to match the word overlap, more or less. That's kind of what they do. They try to match the word overlap with the gold output. And then we also use human evaluation on Mechanical Turk, where we took 50 examples from each of the test set, and then we compare our model that used the common sense with the model that does not. And we give an enthymeme Turkers, were asked if the generated implicit premise was plausible or not. And the agreement between the Turkers, which is a moderate agreement, was 0.56. So these are the results. If you see, this is on the automatic metrics, our model does the best. But again, this is with the caveat that these metrics are not really great. They just look at word overlap, more or less. And then in terms of the human evaluation, when we compare the model that uses common sense versus the model that only uses adaptive reasoning, we see that the plausibility evaluation increases across all the data sets. So it's a promising way to go about it, looking at generating these implicit premises with adaptive reasoning and common sense knowledge. And maybe in interest of time, I'm going to skip this example. We can come back. But these are kind of the main takeaways that I want for you to have, is that even this large language model are called foundational in our field, or are looked at, they are very useful for different tasks. Very blinding using them for whatever you want to solve is not the right way to go. And using theoretical insights about the phenomena you're trying to look at is really important, and using these insights in building your models makes the model better quality. Using common sense knowledge, connotative knowledge, any type of knowledge in the model to plan content and end control in the generation system is important. The open question I have, and I think it's a line we're going to start looking a bit, but again, I think this is one of the open questions, is what other type of knowledge we want, right? And I would argue you want models that are aware of social and cultural norms. Because even when we look at metaphor, right? So when you come in the US, you say life is a journey. I come from Romania. For us, it's life as a struggle, right? So you do use different things depending on where you're coming from. You do need to understand things depending on your cultural norms, social norms, and everything. So I think for us trying to brainstorm, the models are doing now well of including this common sense, maybe this concept net type of knowledge, which is a taxonomic knowledge or word knowledge, maybe even, but going beyond that, I think that's kind of, we need to be building models that are aware about cultural norms to be able to be more appropriate for different, from different culture, people, and so on. And the last point, I would say evaluation metrics and the methods for evaluation are very important. So we can look intrinsically at the quality, task-based evaluation, how they are used and how they are in a particular task, and an end task is good. And I think the open question, and I don't think the community has an answer, is how we can build automatic metrics to evaluate that are able to capture whether your generated output is faithful to the input. Because just doing word overlaps and all the metrics that were built until now, it's really not adequate. And if you want to do human evaluation, that's great, you have to have it, but it's limited. Either we don't have resources, right? You don't have the right amount of people or money to pay large scale evaluation. So how are we going about developing these metrics that allow us to do progress and kind of see what the models are doing better? So the reason these blue metrics and auto overlap were built in machine translation was for the field to do larger progress and see if a system is better than the other. But when you go to this more subtle generation task where you try to really see faithfulness to the input, you have pragmatic knowledge and other things that is not so easy as just word overlap. So I think that's the big research question I think people will have to look into. So just closing words. I started with a metaphor from Kundera. Metaphors are not to be trifled with. And my quote is, theoretical insights, knowledge-aware model, evaluation metrics are not to be trifled with, right? They can give birth to love for generation in figurative language argumentation, NLP in general. Yeah, and anyway, so if anyone from the students interested to get into research in this area, welcome. I just want to put a plug for the course on multilingual language technology, language diversity. We are looking at technologies not only for English, but also for other languages, low resource endangered, and also other translation. For example, a lot of the translation is done on general text, newswire, like web text, not poetry, not poetic, not literary text. And one of the papers we had out of this class was another graduate student doing work on poetry translation. So the class it's great to start doing some research if you're interested in. Anyway, thank you. code and data. We have demos of metaphors. I didn't put it here, but if you're interested to look at that more, let me know.
Excellent. Thank you so much. Any
questions?
I have a question.
Sure.
So you talked a lot about doing various MTurk studies when you were evaluating the output of your models by having people rate the output using different metrics, right? Well, how did you come up with those metrics?
Right. So we did it. We started more from when people are trying to evaluate the quality of a metaphor. So we look at the metaphoricity, the trying semantic preservation, and this is looking at some of the studies that were done before, where people were trying to do metaphors and creative writers. So it was coming from the literature on metaphor and the different phenomena like irony. So they were looking at specific criteria to evaluate the quality of that. And then, so for us, it was also, so the other one, plausibility also comes, and faithfulness came more from the idea of because I think there is a lot of work in generation where, let's say in a dialogue. So you have a dialogue and you generate the next sentence. But that's harder to evaluate. I mean, it's fine, and you might go completely sideways with the translation. What we actually want in our task was, we are in a very controlled environment where we have an input, and we want kind of almost like always a reframing of the input to something else, where we can judge the faithfulness of the generated output to what it was the input as well. So I think that was key for us, like faithfulness, and then the quality, like metaphoricity. And we looked, I mean, one of the points that are a bit more controversial, we also judge creativity, and that's hard to define. It's very subjective, right? So people interpret creativity in a different way. So we didn't really provide a definition. We just let people to interpret what creativity is and how they felt. But that we didn't really define.
What are some of the challenges or current solutions with low resource languages? And by low resource, do you mean like indigenous languages or what specifically?
Yes, so okay, so that's a very good point. So, so language diversity is in a different way. So low resource, the community is using is by the lack of amount of annotated data for NLP, right? So if I'm thinking about developing something for a part of speech tagger, I don't have data annotated with part of speech in that language. So that's low resource. Or for some cases, I have not a lot of presence on the web, right? So I don't have a Wikipedia page. I only have very few data for that. So that's why we mean low resource. This is not necessarily indigenous. That's what, and sometimes they are called endangered languages. So for example, you make a difference in between language typology, like vitality of the language, right? So you say you have a lot of speakers, but not a lot of presence in terms of the technological development. That's low resource. Endangered is where you don't have the speaker either, and you don't have the technology, and you don't. So I think that's, so for the low resource, I mean, a lot of the models, the challenge that there are several things because languages are different, right? So not only the low resource side, what we found was the biggest issue was the complexity of the language. So how complex morphologically, for example, a language is. English is very simple. You break the words, and then maybe you have S ending for plural or singular. So that's quite easy. There are languages we call polysynthetic, which means the whole sentence is in one word. If you want to do anything, you need to split morphology. You need to do morphological analysis. You need to do other things to be able to do any processing on that. So I think the complexity of the language is a challenge. And then, of course, the small amount of data where you want to do anything like machine translation. And there is a lot of approaches for that. When you have, let's say, usually a good machine translation requires million and million, large, maybe parallel data. That's why the machine translation. So you need to have the language, let's say French to English. You need large amount of this parallel text. Low resource, you only have maybe 1,000 or 2,000. So that's a challenge. They have that's in data resources, language complexity.
I'm very curious about some of your research that involves mechanical terms. So can you talk a little bit more about that? And I'm curious about if there's any kind of understanding on by people who are giving their own commentary on whether these metaphors actually reflect their understanding of the language, whether you ask them their familiarity with metaphors and nuances of the English language.
Right, no. Yeah, so that's a very good point. And you see the reflection here, actually, in our evaluation of the mechanical Turk on humans. So let me see if I have the results here. Right. So this was on a scale, let me remember, 1 to 5. The humans were literally experts. One was poet and one was a novelist. So if you look at how crowdsourcing annotated, they give high score, but they didn't give 5. So that gets to your point. We didn't quantify who is actually doing the task of Mechanical Turk. And we are starting now to do that. We are actually pre-screening with a test for a different task we are looking at. So at that point in time, we asked people, and we have a qualifier test to see if they are doing a good job, in a sense of like they don't just copy it. It's like random scores. But we didn't ask them, are you aware? Do you know that? What is your job, or how familiar are we? You literally text. We did not have that control. The way we are doing it now, because we are doing it we try also in the figurative language. We want them to generate figurative language and also to explain why do you think this is an ironic sentence for the literal sense or the metaphoric sense, or for like, so kind of giving an explanation. Here we do qualify, and we ask them, and what we call whitelist. So we give us a small sample of, let's say 10, and then we pick the one that are doing a good job, and we send them email and say, are you willing to do this task for us? So then we also basically whitelist a set of 20 or 30 people that we know they are doing a good job on that. So that's one way to do it. And we didn't do it for this task. No. Yeah.
I'm just curious for the metaphor. So like the example you show us was like it's trying to do metaphoric by exchanging one word and kind of for example generate some metaphoric expression. For example, saying instead of saying the clause like, you say the clause like something.
Yeah. So we did, for this task on the metaphor itself, we only do the verbs because we wanted to give a simplifying, even if the model generates the verbs in the context, so it has to be coherent with the context. We didn't do multi-word expressions. For the simile work we did, so the simile was, it's a type of metaphor where you say, let's say the sky was beautiful, and you have with this comparative, the sky was like a canvas, or the sky was as beautiful, like as canvas or something. So you do have this, we did that on the simile work. So we do have multi-word expression in the simile. On this particular, the metaphor was just the word replacement. Yes, there will definitely, and I think the key challenge there for us, because what we do when we do the generation, right? So we tell the system, you have to replace this word. I mean, you are free to kind of replace other words inside, but that word is the one that you want to replace. And the key point we'll have as a challenge is that, you remember when I said that we build the parallel data automatically? We did it by identifying automatically the metaphoric verbs. Identifying automatically metaphoric expressions or something that is larger, it's more trickier, I think. Yeah, so one thing we can try, I mean, we'll see how to this. I mean, we are one of my students, not with me, but in his internship, he started looking at idioms. So idioms will be another way to kind of looking at larger expressions.
All right, great. Well, thank you so much.
Okay, thanks.